Homogeneity, comparing observed distributions. This is introduction number 2. Now, a couple of things I wanted to clear up from the last lecture. If you have a TI-83 or an older TI-84, you do not have the chi-square goodness of fit test. If you are enterprising, you can go to this YouTube thing, and it will instruct you on how to program your calculator. Otherwise, I'm going to program one at work, and we will pass it around. Now, I want to do the just checkings on the goodness of fit test, which I neglected to do on the last video. So let's get these out of the way. Okay. So this is 681 just checking 2 to 7. You'll be expected to have these done on Monday. Number 2, there are 4. We're going to do the preconditions. There are 4 observed counts of 4 pairs of cells of pairs of traits. That's categorical. You have counts in cells. The expected counts are all greater than 5. 124 students, less than 10% of the unspecified population. It is safe to assume that students are independent of each other. The sample is not random, but we can safe to say it's representative. The hypotheses, null hypothesis. Traits occur in expected proportions. The alternative is that they do not. Degrees of freedom is the number of cells. It's just a one-dimensional table, column of cells. It's n-1, which equals 3. The component of the bottom cell. The component is just like the residuals with linear regression. It's actual minus expected divided by, in this case, actual minus expected squared divided by the expected. So that's approximately 1.66. And the p-value of the chi-square statistic, calculated chi-square statistic, 6.64. So we could do 6.64 comma 99. It's always one tailed to the right. It's skewed. The shape of the distribution is always skewed. Comma 3 degrees of freedom, and we got a p-value of 0.0843. And the conclusion with a p-value of 0.084 above 0.05, we failed to reject the null. There is no evidence that the population deviates from the expected distribution, genetic traits, etc., etc. Okay, so the next part, homogeneity. Comparing observed distributions. The chi-square test for homogeneity compares how 2 or more different populations differ in how they distribute for a categorical variable. The null hypothesis is that the populations do not distribute differently. The alternative is that they do. Period. No symbols are involved. We have a symbol for the test statistic. The test statistic calculated the same way. But we now have a two-way table with the different populations in columns and the subcategories of the categorical variables in the rows. This is a frequency table, not a relative frequency table. It's an absolute frequency table in that the actual counts are in the cells. So we can't have percentage expected cell counts are based on the marginal totals in the table. In the book, the example concerns 4 colleges at a university, 4 different populations, if you will. The colleges make up the columns. The categorical variable that the university officials are interested in is postgraduate choice. There are 3 subcategories for postgraduate choice: employed, grad school, and other. So here's the table. Now this is a 3 row by 4 column table, 3 by 4. Now let's remember the margins, like the labels or the numerical totals, are not part of the table. This is not a 4 by 5 table. It's a 3 by 4 table. Okay. So there are 448 agricultural students, as you can see in the margins. The overall proportion of students surveyed that chose employment, as you can see in the margins, is 685 out of 1456. So the expected number of agricultural students that chose employment is the total proportion that chose employment times the number of agricultural students. Total proportion that chose employment, 685 out of 1456, times the total number of agricultural students. Now this is the sort of thing you would be expected to do by hand during a test. They ask you, what's the expected, the amount, and then later on you have to come up with the component. So 685 out of 1456 times 448, about 210. Okay, the component of the chi-square statistic for the employed agricultural cell is the actual minus the expected squared divided by the expected. Actual minus the expected squared divided by the expected, or around 1.5%. The cells in the table hold the counts and don't include the margins. The degrees of freedom is rows minus 1. This is for any two-way table, definitely for any test for homogeneity, and we have another one that uses the same approach for independence. Rows minus 1 times columns minus 1, which is 3 minus 1 times 4 minus 1, or 2 times 3, 6 degrees of freedom. Chi-square test is the sum of the chi-square. The chi-square statistic is the sum of the chi-square component for each cell, just like the goodness of freedom test. So let's do the test. P, problem in context. Okay, we want to know if the postgraduate choices made by university students differ from college to college. Okay, at this whatever university this is. Hypotheses. Postgraduate choices made university students not to differ. They do differ. Okay, notice there are no symbols involved, but we do have there's an assumed population parameter. They don't differ. They do differ. Assumptions. Data is categorical. Counts of students in each cell. 1456 is less than 10% of the total students in university, we hope. Expected cell counts all exceed 5. How do we know this? Okay, now, once you're dealing with the chi-square test for homogeneity or later on for independence, you have to actually run the test to find out what the expected counts are. Unless you want to do them all by hand, which you're welcome to do, but I don't encourage it. All right, so let's run the test. And so I'm going to take my calculator here. I'm going to reset it, restore the default state. Yes. Okay, the way you run it is by putting this table into a matrix. All right, so we're going to hit for the matrix hit the second key and then hit the inverse key, which puts you into matrix, arrow over to edit. And we're going to put our data, our table, into matrix A. Now the matrix of dimensions are measured in rows by columns. So this is 3 by 4. Now make sure that your matrix looks like the matrix that you're working with with your problem. So this matrix that I just made is 3 by 4. 3 rows, 4 columns. If I had 4 rows and 3 columns, I'd know I'd put the numbers in, and then I would go and reverse them. Okay, so just look, use your eyeballs. You got 209, 198, 177, 101. Notice that the whole matrix doesn't fit on the screen once you get 4. It only shows 3 columns at a time. And of course it goes horizontally. Okay, now I'm going to check my numbers. The third column, 101, 33, 16 looks good. 177, 158, 39 looks good. 198, 171, 15 looks good. 209, 104, 135. Okay, so my data is good. All right, so when I run the program, it will automatically calculate the expected amounts for me and put them in matrix B. You don't have to touch matrix B. Doesn't matter what's in matrix B or what its dimensions are. The program will take care of everything for you. So I'm going to get out of here. I'm going to go to Stat and Tests, and I'm going to arrow down until I get to the chi-square test. Now, whether you have the goodness of fit test or not, you will have the chi-square test. And that's it right there. Now, there's the goodness of fit test. You don't want to run that. Chi-square test, hit Enter. Now, it expects the observed to be in matrix A. You could change this. I don't recommend you ever try to change it. Okay, just always put your observed amounts in matrix A. You don't have to touch B. It will take care of B for you. It will put the expected amounts in B. You arrow down to calculate, and you hit Enter. Okay, now here's our results. Chi-square statistic. In other words, that's analogous to the t-score or the z-score is really big. Now consider, we have 6 degrees of freedom. That means that 6 is the mean, and the mode, that's the hump on the skewed distribution, is 4. And this is 93. So this is far, far, far to the right of the mean. And you can see the p-value is effectively 0. 5.26 times 10 to the negative 18th. So in other words, point, and then write 17 zeros, and then 526. And there is your p-value. Okay, so you can see we're going to reject the null. But anyway, but first we have to satisfy our preconditions. So we have to look at matrix B and make sure the counts are all good. So I'm going to hit second, and then I'm going to hit the inverse key, and I'm going to go over to edit, and I'm going to look at matrix B, number 2. Okay, now you can see the first column's good, everything's greater than 5. Second column, everything's greater than 5. Third column, everything's greater than 5. So I'm going to arrow down, and I'm going to go over to the fourth column. And you see the fourth column, everything is greater than 5. So the precondition is met. Okay? So the assumptions, and here's matrix B. Run the test. We looked at matrix, here's matrix B, and it shows all the numbers. Okay. The expected count for each cell exceeds 5. The sample is not random, but it's safe to assume the students are independent of each other. Name the test. The preconditions are met. The sample is a chi-square distribution of 6 degrees of freedom. Perform a chi-square test of homogeneity. Test carried out. Well, you don't have to, there's nothing for you to show really, except you got to write down these results, which I have here. The calculator will draw a picture for you, and on the right it will show the shaded area where the p-value is. Of course, the p-value is 0, so there's nothing shaded. And with this huge chi-square statistic, the p-value is quite small. And here's the p-value. I took just for fun, I typed it out. Make a decision. With the p-value effectively 0, less than 0.05, the default alpha, reject the null. State the result in context. There is evidence that the postgraduate decisions differ from college to college. Now, we're going to analyze the results. We have residuals with this. So in other words, some cells differ from the expected much more than others, like the agricultural guys. Remember the agricultural people? Where were they? Up here somewhere. Yeah. They hardly differed from the expected at all. Okay? So they did not contribute. If all the other cells were the same, we would have failed to reject the null. Okay? So some of these cells, must have had huge differences. And we call those differences residuals, just like we did with linear regression. Okay? And we use the observed minus the expected, just like we did with linear regression, to calculate residuals. So the standardized residual, we call them standard. We're going to standardize them because we're going to divide it by the square root of the expected. It's symbolized by the letters lowercase italic c. So the standardized residual for a given cell is observed minus expected divided by the square root of the expected. Now the standardized residuals are z-scores and can be understood as such, which means they measure how much a given cell differs from the mean. Okay? Now, you can only compute them by hand as of right now. I'm working on it, but I don't know if I'm going to get there in that. Okay, I've been looking around for programs to do this. One of you sharp young guys or gals can figure this out and get me going. So anyway, but if you come up with something, let me know. You can subtract matrix A from matrix B and store it in matrix C, for example, and get the numerator of the standardized residual. In fact, let's do that right now. I'll just show you how you can do that. Let me get out of here. Let me clear the screen. So what you would do is, so we want to do actual minus expected. Okay, so that would be A minus B. A is the actual and B is the expected. So I would do second and inverse, and I would put matrix A into the work screen, and then I would put a minus, and I would put second and inverse, and then matrix B, so I'd arrow down to 2, and I would put that, and then I would store it in matrix C. 3, matrix C. Okay, so I hit enter. All right, so now we can go to the, let's look at it. I can look, it's easier to look at actually inside the program. So I'm going to go to edit, and matrix C, number 3. Okay, now you can see the really tiny difference from the difference, and then but some of them are really big. I haven't figured out. So this is the numerator, but I haven't figured out a way to divide each one of these cells by the square root of the expected amount for each cell. That would be a nice thing to do, but I don't know how to do it. Anyway, it requires some programming. But at least you can get the numerator, and you can see, wow, some of these cells are really, really different, you know, and you can see where there's a lot of big differences here. Okay. Now, probably the typical thing you would be asked to do is just to compute the residual for one cell. So you need to know how to do the residual. Now, here's all the residuals for every cell. So let's look at them, okay? Now, let's look at the row for other. Clearly, agriculture with a big positive z-score, 4.2, was most interested in going off and going on a trip or whatever, and engineering was least interested in it. And as far as going to graduate school, engineering, those guys were gung-ho about graduate school, and agricultural was really turned off by it. And in terms of getting a job, the industrial labor relations people are all crazy about getting work, and the arts and sciences people not so much. Okay, so that's our analysis. So it's kind of interesting. Let's do the just checkings. Why do we have, we're talking about the potato beetles, and they do an experiment, and they have 3 different jars, and the one jar they have spraying with water, and then they have natural spray, and then they have insecticide, and then they live and they die. Okay, so why do we have a jar with water? Well, we want to know how long the potato beetles live in the experimental box. So as a baseline for comparison. Okay, 9. The null hypothesis, it doesn't make any difference. There is no difference. You know, it's the same deal, same stupid null hypothesis stuff we've had all throughout the course. Nothing changes. There's nothing new. Okay, 10, degrees of freedom. Okay, so we have 3 types of treatments. We have 3 treatments, and we got 2 outcomes, live or die. So it's 3 minus 2 times 2 minus 1, 2 times 1, or 2. 2 degrees of freedom. Okay, the expected count for natural spray survivors is the total number of survivors divided by the total number of beetles times the number of natural spray insects. 125 over 500 here. Let me look at that again here. I don't think I'm saying this right. Here, let's go. Okay. Yeah, here we go. So there's a total number of 200 natural sprays. 125 out of 500 survive. So let me go back to this thing here. Yeah, 125 out of 500 times 200, and that's 50. Okay? So 50, we expect 50 to survive out of 200. In other words, 1/4. 40 beetles survive instead of 50, so the chi-square statistic is 40. The actual minus the expected square divided by the expected, which turns out to be a nice even number 2. Okay, degrees of freedom is, so suppose we have a chi-square statistic of 10. Would you expect a small p-value? Well, the degrees of freedom is 2, and which is the mean, and the mode is 0. Okay, in other words, right at the beginning, practically. So with the mean of 2 and a chi-square statistic of 10, 8 beyond the mean, I would say that is a big p-value. I'm sorry, a big chi-square statistic, which would mean a small p-value. All right, so do problems 12, 27, and 29 based on the chi-square test of homogeneity, and watch the next video. And that's it.